I don't think Alex is traveling to Drexel for a talk, but I'll make it to. Hey, are you still there? I think your frame is frozen.
Oh, that's curious. I'm still here. Yeah, I can hear you.
Oh, okay. Right. I guess we can start. Uh, it's a great pleasure to have Eric Rodriguez from Harmonic with us today. He's going to tell us about searching for formal proofs. Eric, please take it away.
Lovely. Thanks everyone. Thanks for having me. It's a real shame I can't be there in person to join you guys, but it's a little far from London, sadly. So yeah, so I think let me start sharing my slides if I can. I did practice this, but all right. Can you guys see my slides? Yes?
Yes, we can.
Lovely. So yeah, so what am I going to be talking about today? So computers can already prove non-trivial theorems, and I mean, for me, I'm mostly interested in doing so in Lean, for some reasons. I'll talk about later. But I just want to step back and sort of like realize this is like quite amazing, right? Like, I think most of the talks I've seen in this seminar, um, I've said so far, like, oh, like as we know, like computers can prove theorems and can prove theorems now. So like we just need to, find new theorems or, you know, talk about theory building, like all these things. And I don't disagree that they're really interesting, but I think also it's worth thinking back to, 2020. If you showed people like what we have today available in terms of like proving theorems in any sort of system, like proving theorems automatically, I think that'd be just say it's a straight up science fiction. So I think, yeah, it's truly quite amazing how fast and how far we've come. And so I want to take a step back and sort of look at that and like try and peel back some of the mystery of how computers are proving theorems, why they're doing it in Lean, right? And how like are we and then I want to look a bit to the future and like see how like people are using these things now and like how we can like get more use out of them later and all that we've done so far. Um, so I'll just start with the first stuff, which is lean proof search in Aristotle. So Aristotle's a system that like works with lean proofs. So the input is just some lean statement. So something like can you guys see my mouse by any chance?
Yeah.
Yeah. So something like at the top, or well, like the theorem statement at the top, and it will hopefully write a full proof thereof, right, of the subsequent of the whole theorem, right? And the core system, the really like the first level to doing these things is literally just to take a theorem with some gaps, right? So that would be we mark these gaps out with sorry and progressively fill them in. Right? This is sort of how a human interacts with lean, but I'm going to explain a little how our system is a little different in that, and like the interaction is perhaps a bit less flexible than you expect, but it allows us to do to search in a very like in a much more amenable to computers way. Anyways, um, and so okay, so if I'm searching, I need some sort of like map, right? So like a tree structure or a graph structure, and so um, this is the first thing we want to define. So So as I said, our input is a lean file or a code block where sorries are containing, where sorries needing proof are missing, right? And what we want to do is from each state, which is just individual lean proof states, that would be any of these squarish things here. We want to find tactics or actions, as if we're sticking to the sort of nomenclature, um, which get us closer to a proof of this theorem, a full proof of this theorem, right? Um, and so, okay, we it's fine if we have our inputs, we have our states, but how do we generate these actions, right? So this is non-trivial, but like perhaps you can think, oh, like you can just use an LLM, right? Like this is, and indeed this is what we do. We ask an LLM, especially prompted LLM, especially trained LLM, to fill in and give us some of these sequences of tactics. So, for example, just this intro here, right? Or this cases H statement with another hole in here. So there is an implicit hole. A very explicit hole here, saying like, hey, like I'm not giving you all of the proof. I'm giving you just a little bit of the proof. And I can worry about that later. So this sorry here maps to this next state, right?
Does your
And
approach fix stories? Like they're generating the holes?
sorry.
Your approach, are you when you generate a partial proof, are you generating the sorries or are sorries filled in afterwards?
Yeah, so there's sort of both, right? So so we the sorries are being generated by a language model by sort of saying, and they basically end up meaning like, look, there's more work to be done here. I shouldn't do this right now. I should leave this all to be done later, right? Later on in the graph, and then sort of assemble together. So you can see like if you look at this sorry here, if you look to the left, right, this is replaced with the sort of implied proof from all of the other tactics or well lean little bits of lean code, right? So you see we substitute them in and you end up with like a proof with no sorries, right?
Yeah, but you can also imagine an approach where you are not predicting the sorries, you predict like a whole proof, and then you fill in the sorries for every portions of code, right?
Yeah. I mean, this is certainly an approach that one can take, and I think systems like SeedProver, etc., do some approaches. But I'm just here. I'm just highlighting what we've done, and I mean, we do take some version of this approach, and I'll touch on that a little later. So, okay, so we got the states, we got some way to generate the actions, right? And a little to our chagrin, right? Like there's a little more complication. First, you can't just apply a normal like tree search algorithm because as we saw earlier, we have some tactics that can branch into multiple states, right? And so like to solve the whole problem, you actually need to solve every possible follow-up state, not just one of them, right? So you end up having like a search hypertree instead of just a tree, and you have some sort of and/or structure, right? Like wait, you can imagine that there is other like possible tactics you could explore here, and we ended up with only these. Sorry, and we want to select the or, so that, and by or I mean like we want to select a tactic that leads us towards an end, right? So a state where there is no goals, these empty blocks. But there is also an and structure where, like, okay, when there is multiple goals that you need to solve all of them to actually have a valid proof. You can't just solve this left-hand side, you also need to solve the right-hand side. All right. So to add like even more complication to this, there is also not structure. So what we, just to further add complications, we go back here. We also have implicit nodes, or well, I think the terminology starts breaking down, but you can start searching to see whether a state is true or false, right? And this allows us to prune states. I'll sort of come into talk about that in a bit. But okay, where does this end up, right? So we have some sort of graph-like thing that you can traverse, right? And the way you traverse it is by like starting at a state and asking an LLM, hey, generate to me some tactics, right? And then plug those in. Some of them will error, some of them won't work, some of them will do nothing, right? And then you can just keep going from there, branching out further and further and further. But this will like quickly become like completely untenable, right? Like if you are branching out even like two leaves per node, right? Then 5, 6 layers deep, you're already at like some humongous number of states tactics. So we can't do that. We can't just apply something like breadth first search or depth first search. So the way we explore this graph-like structure is with a Monte Carlo, well, not tree search, but like a graph search approach. And so what does that mean? That essentially means that our system not only has to pick which nodes to it doesn't pick which nodes to explore in like a deterministic fashion, like a breadth first search, like a depth first search, but instead it will try and it will find the node that it thinks is the most promising, that it has the most potential to lead you towards a proof, and expand that. And by expand, we mean go and query the LLM, say, hey, give us some tactics here. And okay, so what do I mean by the most potential here? So to figure out what most potential means, you need to have a notion of a value function, right? And so what this means specifically here is, do we expect this node to be provable, right? So the node with, say the Riemann hypothesis, we would expect our value function to be close to 0, right? But a node that says like x plus y equals y plus x, we would expect that to have a value function that is very, very high. And so you end up with a notion of how easy a node is to prove. All right, that's the first half. But that's not it, right? Like you can generate lots of very easy nodes to prove, right? Like you can, for example, start writing have statements that like say trivial things like, oh, prove to me that 2 plus 2 equals 4. Okay, sure, that's an easy thing to prove, but it doesn't add very much to your search. It doesn't really help get you towards your goal. So you have to sort of counter this. I mean, you have to counter this, and you counter this in many ways. So maybe perhaps let me see if I can switch to another sharing screen to give more of a live demo on this, on exactly what I mean here. System share. All right. Can you guys see this? So this is just a little lean interactive thing that allows me to type in tactics, right? Can you guys see this?
Yes.
Yeah. Okay. So I was saying, like, you can write something like, okay, have 2 plus 2 equals 4 by sorry, right? That's some tactic that you have. And so, okay, so then you get 2 goals from there, right? So You have this goal 0, which says, okay, 2 plus 2 equals 4. That's really easy to prove. And then you have your original goal plus the hypothesis 2 plus 2 equals 0. Now, this goal is really easy to prove, but to actually close the whole thing, you need to close both goals, right? So your value function would look at this and say like, hey, even though goal 0 is really easy to prove, goal 1 is perhaps like equally hard to prove, right? Like this adding very simple thing does not change the provability of this more complicated expression, right? This relatively more complicated expression. So when you have to solve a multi-goal state, what you actually have to do is you have to select the hardest goal, right? So the goal with that has the lowest value, and this would be the value of like the combined goal state, if that makes sense. Does that make sense to people?
Yeah.
Yeah. Cool. So if I go back to my slides, so
Eric, can I ask a question?
yeah, go on.
Yeah, can you comment on what the value function is when you're doing RL for lean? Is it just like -1 for each step taken and then a large reward for completing the proof, or is it more complicated than that?
Yeah, I'll touch on that in a bit, but yeah, we train it based on the binary reward. So it's yeah.
Whether you prove.
Sorry?
It's just, I guess, binary meaning whether you prove the theorem or not.
Yeah, exactly. Right.
So you don't penalize it for the length of the proof. Like it could prove 2 plus 2 equals 4 in like in 10 lines or 1 line. So you don't penalize it for taking 10 lines instead of 1.
No, but there is an implicit sort of penalty here, right? Like in that because you are well, if you write 10 lines but in one step, right? Then no, this is exactly the same as like writing 1 line. But if you write 10 lines in 10 separate steps, then there is an implicit penalty that your exploration just won't be able to reach. Like it's unlikely to explore that deep, right? Like because you only have a specific budget for exploration.
Right.
So there is not an explicit penalty for such proofs, but generally, like because of like the externalities of the system, right, and like the situation it finds itself in, you end up favoring shorter proofs. You end up favoring like slightly more compressed proofs, and some of you that have seen Aristotle outputs have seen that it often like combines tactics in certain ways. Like my, my take is that this is not actually due to like this is just an optimal thing for the system to do without any sort of nudging of rewards, right? Just yeah, due to the limited budgets.
Yeah, this is really interesting because I was thinking if it sort of penalized for every additional line of code, then the agent would just learn to use the most powerful tactic at every step, like omega or whatever the most
Right.
powerful is. So maybe there should be a penalty for using powerful tactics so that it sort of maybe learns to use intermediate lemmas and theorems from mathlib instead of just using the most powerful tactic in each stage. Yeah.
But I mean, I think in some way, right, like you don't care if it uses a powerful tactic, right? So I think you're right that like to have maintainable code in the future, like generally, like you don't want to use like really expensive tactics that like are, yeah, that are brittle or that like are sledgehammers to prove very simple things. But once you have a proof, it's very easy to go through and sort of systematically like update the proof
That's
to
right.
remove such occurrences, right? But it is less easy to find the proof in the first place. I think generally I'd favor finding the proof and then dealing with such things as opposed to trying to optimize for style explicitly.
I agree.
But there's many variations on this. So for example, alpha proof explicitly uses a length penalty. I'm aware of this. So
Right.
sorry, was there another question?
Yeah. So is this value function an encoder with a linear head on top of it?
Sorry, could you repeat that?
Is this value function an encoder with a linear head on top of it?
With lean ahead?
Linear head. So I use a decoderly model, and I replace the LM head with a linear head just to give me the binary rewards. Is that how this is trained?
I'm really sorry. I don't know if it's a microphone, but I can't hear you very well. But
He's saying linear head. Linear, like a line. Linear.
oh, I don't think I can go into that sort of detail. But I will touch on roughly how this is trained. In a second, like the data that we use, I can touch on. So, okay. Cool. Let me just skip to these slides then, as people are asking. So yeah, so as people are aware, we use reinforcement learning with some sort of binary reward to prove the theorem, and we do train the model to we train the model to create tactics that we found in successful paths. And I want to note paths here. Like this does not mean a full proof. This can mean like little sections of a proof, right? Like, so for example, in my toy example from earlier, right, that 2 + 2 = 4 proof could be used even if I didn't finish the whole overall proof, right? This is because it's sort of like a sub path of like the whole proof, if that makes sense. And the value function we train based on the successful and unsuccessful paths, whether that be of like entire proofs or whether that be of subproofs. And so our positive examples are just, things that we managed to prove eventually. And our negative examples are things that we either found to be false or that we have tried quite a bit. And so we expect that therefore it's probably not true, or at least that our model can't prove it, right? So this is not the strict value function of like an optimal policy, right? So the strict value function would be 1 or 0, right? Depending on whether like it is possible the statement is true or false. But we instead are just training towards the value function of like what our system is at the moment. And one interesting thing that we can do, and we did during the IMO, is to run this training loop for specific problems only, right? So we generally run this training loop for like only for every data that we have, right? Like we combine that data, we do some alchemy, choose some coefficients and choose what data to mix in where, etc. But if we really want to try hard on a problem, we can actually run this training on data that we have collected from that specific problem, right? And so this helps us like build like a version of the model that is like specifically suited towards, I don't know, IMO 2025 problem 3, right? And this synergizes very well with the lemma-based informal reasoning pipeline, which I'll come back to discuss in a sec. Yeah, does that help with your question about the value function?
It does. Thank you.
Yeah. Any other questions so far? Lovely. Yeah. So another way that okay. Let me sum up where we are right now. So we have this system, right, which is just a system that takes in many technically, but it takes in code with lean sorries, and it tries to find proofs to those sorries. It tries to replace those sorries with a proof of some form, and it finds this proof using Monte Carlo tree search. This system is very, very, very good at what it does, and it's like frightening quite how good it's become. So I joined the company just over 2 years ago, and when I joined, this system was not able to like interchange summation and like products. It was like incredibly bad, and now this system is incredibly capable, like in and of itself. Like it is shocking. Like I think I'll be happily to say that this system is better than me at solving any individual sorry and lean. Like it is, and much faster too. It's quite impressive seeing it leapfrog. But I think one thing that we observe is that this system cannot sort of start writing sort of more general statements, right? So like the way you structure a proof in lean is not generally to just put everything into one theorem, right? Like you really want to have, so say for example you have a definition, right? Like you want to prove basic things about this definition. Okay, what is the definition of this definition? What happens when you plug in 0 to this definition? What are sort of the inductive properties of the definition? By that I mean like, okay, like what is like, how does this definition behave? So if it takes in sets, like how does it behave under unions or intersections or whatever, right? Like, so you want to develop the API. But also like sometimes it is easier to structure things in separate lemmas, right? Because there is some facts that you use multiple times during the proof, and it's in theory possible to write these in line in your lean proof. But it's quite unergonomic to do so, and really not like in the style of these systems, or well any code that they've been like bootstrapped off or whatever, right? So generally we see that these systems improve quite a lot if you feed them with additional context with lemmas about the thing that they're trying to prove, much like a human would. And so another way that we can improve the performance of this system is to add like an informal-ish pipeline around this proof search that helps you that generates lemmas and generates like possible subtasks to work on to then lead you towards your final goal. And so the way the system works is very simple. So you ask a model to generate some informal proof sketch of the target theorem. It doesn't particularly matter whether it's right or wrong. We'd like it to be right, but I think if all these systems were right automatically, we'd all be out of a job. So we're not there yet. And then we break this sort of informal proof into like a sequence of short lemmas, right? So just like lemma 1, like this definition does this under this circumstance, blah blah blah. And then you take those lemma statements and you put them into lean, and you do some like automatic fixing. You go back and forth. You give the LLM, hey, like this is what happened, but this is what you tried, but the compiler says, oh, perhaps this is wrong, or you missed like a type description here, anything of the sort. And you have a small little loop to try and fix some of these type errors. And then you pass these to the very same search system that we were just discussing, right? And because these are much smaller lemmas, these are much more bite size, it's a lot easier for the search system to prove these lemmas, right? And start proving things about the proof sketch, or like part of the proof sketch, right? And it can reuse earlier things it's proved to try and tackle later ones. Just as you would in a lean file. And then you try again at the main theorem, right? You see, okay, here's some lemmas. I managed to prove like, so say maybe there's 10 lemmas, right? I managed to prove 7 of them. 2 of them were actually negated because the the LLM that generated this informal proof was wrong, or maybe it was misformalized or something of the sort. And one was not proved. So we, might be helpful, but we can't use it because it's not been proved. And from there, you try again to prove your main theorem. And you can sort of keep doing this iteratively, right? Sort of expanding the informal proof where needed, or you can fix up some lemmas that were like proved wrong. Anything of the sort. Like the action space is a lot bigger, right? Because so if you think about it, the previous system could not explicitly like erase, right? It could not say that like, oh, like this tactic I took was a bad tactic to take. It's made my goal worse, right? Like you can sort of implicitly do that. Like if your value function thinks that it's a bad state, then it is likely that your state will not be visited very much. But you can't explicitly sort of say like, hey, like actually this is a really bad tactic. Like I don't want to be I don't want to do this. Or perhaps sometimes like the theorem might be too hard, right? Like, and it's just it might not fit within the budget, right? So this gives the system a much wider action space, right? But it's it can revise the list of lemmas whatever way it wants, but it's not as effective. It's not as good because it's the system is less constrained. I think with more constraints, it's easier to make a system that like can perform well because in a constrained environment, like what I mean by this is a constrained system is easier to optimize for, right? But is inherently just less powerful and less able to do more things. And sometimes you need to be able to do more things. Yeah. So you can go back and forth with this. And I'll just say another thing real quickly, which is that this training loop that I mentioned, right? It doesn't just have to be on attempts on the main theorem, right? It can be on attempts on these lemmas, right? And we found that like using this training loop, like this RL training on specific problems, or like, well, lemmas generated from a specific problem, was super, super key to the things we did. Like it made Aristotle, like the key Aristotle search system, a lot faster, but it also allowed it to prove more things. So win-win. Yeah. Is there any questions? I feel like I'm hearing a bit of.
How do you decide what is successful path and an unsuccessful path? Do you first pass it to a model to generate the tactics and then use FCGS?
Are we passing what? Sorry.
So how do you first create these successful and unsuccessful paths?
Uh-huh.
Like my understanding is that you might initially you won't have a trained value function. So how do you choose the tactics in the MCTS to come up with the successful and unsuccessful paths? Or is there a different approach that you're following?
I'm not sure I can say how we bootstrapped it, but effectively, right? We are in an expert iteration sort of loop. So at some point, our value function is good enough that like between different like model versions, like it's pretty good. Like it's good enough to that like this mismatch does not heavily matter. Yeah.
So there is some warm up involved, is it, for the value function initially?
Yeah. The value function did not just appear out of nowhere. Yeah.
Okay. Thanks.
All right. Yeah. So okay, skipping forward a little. So this was the version of Aristotle that we used at the IMO. It's in 2025. Aristotle since then has changed quite a bit. Aristotle is now an agent, which I have spent much time on with others at the company. And Aristotle has done many things. So there is Erdos problems has been talked about ad nauseum. Aristotle has certainly solved a fair few of them on its own. It's collaborated with other LLMs to solve many others. I think for my colleague, the latest numbers I have is that 105 out of 115 Erdos problems that have been formalized in Lean have used Aristotle in this process. So the vast majority of formalization activity on the Erdos problems website is through Aristotle itself these days. There's also sort of efforts going around sort of verifying other things. So on the right, there's this tweet from Ilya Sergey where he verifies a memory allocator with Aristotle and other tools, which is pretty cool. But yeah, I sort of want to focus on the case on the left here, right, where there was this Erdos problem number 650, which was solved a few weeks ago, but not in any sort of clean way with just Aristotle wrote a simple proof or OpenAI just wrote something. No, it's a bit more interesting than that, in that GPT provided some sort of proof, which was then fed into Aristotle to be like, hey, let's try and check this. Let's see if we can try and verify that this very long, detailed proof by GPT 5.4 was good. And I mean, I think it had human review previously, right? But I mean, A, it took a while, and B, they missed the detail. This proof was actually wrong. GPT's proof missed out an edge condition with some injection used within that meant that for the vast majority of cases it wasn't actually an injection. But Aristotle noticed this, fixed it autonomously, and didn't tell anyone, right? It didn't take any credit. It just sort of said okay, here's your proof. It's slightly different, and it ended up being slightly different from the GPT proof. But it just fixes errors autonomously. And I think, I don't know, it points to an interesting world where we're just going to see we're going to see systems generate, more and more things. I think everyone is inundated with AI text messages, AI emails, AI everything, and it's hard to sort of filter out the noise from the valuable. Certainly there is things of value in there, but it takes a lot of time to actually filter these out and see if these systems are telling the truth. And so I'm just honestly convinced that we will not be able to scale this much further without better oracles for knowing whether a claim is true. So in maths and perhaps in software, verification, Aristotle, could be a path forward, and I think it will be the path forward, right? But I think it's more interesting to see as well, how will that evolve in other domains, right? But yeah, I mean, I don't really have too much more today. I know that I'm a little under time, but I'm happy to chat and have some questions. It's available for free for everyone to try, Aristotle, and I think people should make good use of it. It's really quite powerful. I don't know of any system that's this powerful and that's freely available in many other ways. So I'd encourage people to just toy with it, see what they can do with it, and most importantly, let me know, because I find it super cool seeing what people do with it, or hearing complaints about the system. It makes it a lot easier to actually improve it, because I myself, like, and many of my colleagues have lots of time to make the system, but that means less time to sort of, use it as a mathematician would, see what goes well and what goes wrong, and and try and unify it with other systems and see how that happens. Like, I think some of the biggest performance improvements from our system have come from like sort of fairly not obvious, but like small tweaks or fairly small ideas. So I think you guys can get very good output out of Aristotle on its own, but I think you can make it even better just by toying with it and using it within I don't know, other agentic frameworks, or like unifying it with other tools. And I'd be very, very keen to hear about such things. So yeah, um, that's all I prepared. Any questions from people?
Well, let's thank the speaker.
I have a question. So, how's the Aristotle's performance on math theories beyond MATLib?
Mm-hmm.
Yeah, have you tried anything like that?
Yeah. So this Aristotle agent is fully able to develop theories in and of itself. These Erdos problems, formalizations are just like small examples of theories, right? But people have been like working on, more larger coherent projects over many runs of Aristotle. I've personally been using it to try and formalize some stuff about hack games, which was one of the things I worked on um, when I was in my undergrad. I know Alex Myberg has been working on it with quantum theories. I think not quantum computation. I don't quite remember the specifics, but yeah, the hope is that we can build theories with Aristotle, right? And I think one thing that's really interesting about building theories with Aristotle is that I think the verification problem is a lot easier to solve than people expect, right? So I've seen a lot of worry from people saying like, hey, like, I'm fine with a computer solving my theorems, right? This is completely verifiable, makes sense, right? But suddenly if my theorems have bad definitions, right, then I can't actually say anything about I can't be sure by just looking at like the theorem statement, like, oh, is this proof actually correct? Because now I have to look at the definition. It might be like really subtly wrong. Like, yeah, and this is true, right? Like this is not false. That definitions can be subtly wrong, but I think as these systems now have like as I said, like the action space is now even bigger, right? Like Aristotle agent is really an agent, has a larger action space than any of the systems that I mentioned, that I explained today on the talk. They are able to sort of autonomously run these sort of checks and balances, and I think they have to, right? Like they have to converge towards a good definition, because if they don't, they won't be able to solve the problem, right? So take, for example, Fermat's last theorem, right? Say that you reached a proof of Fermat's last theorem that with some coding agent, right? Like we scooped Kevin Buzzard somehow. We
I'm sorry to interrupt, but if I may have two more questions.
Yeah. Sorry, go on.
All right. Yeah. Thank you. And so one small question is, in my experience with Aristotle, it spams too much ASOP, the tactic.
Mhm.
Can we somehow reduce this, or is there a parameter we can choose to not let Aristotle use ASOP all the time?
Yeah, you can tell Aristotle not to use ASOP, and it will try and remove it. It's
Okay, cool.
this is one of the benefits about the agent model.
All right. And when can we run Aristotle like cloud code where we can see something happening in real time instead of waiting the progress bar to reach 100% and see the result?
Yeah, I can't say anything on this right now, but
Okay.
I think people will be very happy soon. That's what I will say.
Yeah, right. All right, great.
Um,
Thank you.
so I'll just quickly finish my point, which is that say that we had a proof of Fermat's last theorem, but the definition of like the Hecker operator was wrong or anything like that. The proof of Fermat's last theorem still stands. Like somehow, like even though the definition is wrong, like we still prove the right thing. So maybe that's an alternative definition, or otherwise, like if the definition is very flawed, then I think the agent will discover, hey, like I'm not able to prove any of the theorems that I need to prove, right? It won't be able to get to sort of a landmark theorem, a theorem that doesn't depend on these definitions or depends on more simple definitions. And so that's like one way that you can think about sort of verifying definitions in theory building without having, without just having to go through them manually. Yeah. Anyway, sorry. Any other questions?
Yeah, I wanted to ask, and so you've mentioned a couple of times in this talk that part of your goal at the moment is to get Aristotle to be used by people. One of my main concerns for using Aristotle is it's free now. How long is it going to stay free? Do you have any idea about that?
I'm afraid I don't know. I don't have any hand in the biz ops, but I think we want it to stay free for for academics for as long as we can. Like
That's good to hear. And I have another very silly question, but I think this actually matters to adoption. I've spoken of Aristotle to a number of my colleagues, and two completely independent responses that I've gotten were it seems weird to use a tool named Aristotle, given that Aristotle was the one Greek scientist who seemed to have been wrong about everything. So why the name Aristotle?
Yeah, I mean, if I'm honest, I don't know. I mean, internally, this system was called Module D. So,
It may have been
uh,
that.
yeah, perhaps when we release our new model, it will be called something else. Yeah, again, that was a decision that was made by more marketing people than me.
It can seem silly, but I think that this can make people trust it or not, depending on what their preconceptions on actually are.
No, for sure. Names are very important, I think.
I have a question. So you're talking about also like scaling to maybe more complex problems. So in that, I guess, what do you foresee as the bottleneck? Is it the data that you have available? Is it this auto formalization plus decomposition plus proof search kind of thing? Like I guess, or something else that I'm not thinking.
Yeah, that's a good question. I think right now some of the bottleneck is sort of building. I think it's been quite interesting sort of seeing the complete like completely huge amount of ideas that are like within the company for ways to improve Aristotle and many ideas that we're like fairly certain that would be profitable, right? Like sorry, not like profitable in terms of like improving the performance. But we just don't have time to actually build them out and run them. So I think, on a simple level, some of the bottleneck is just building out things that we think are going to work. But I think more fundamentally, what is the bottleneck in the long run? I think it's really hard to say. I think if I knew that, I would be an investor in a VC, because it's yeah, as I say, reinforcement learning has been incredibly, incredibly effective. And I, unlike, sort of training on human data, there is no inherent reason on why it has to stop, right? Like these systems are not like just learning based on what humans know. Like they're legitimately learning on their own on or based on new things. And as we've seen with like AlphaZero, like they can surpass humans, right? So yeah, I guess on that, like the one sub point that I find interesting is that rollouts for reinforcement learning like are now longer and longer, right? So if we think of the famous METR charts, right, like frontier models in like coding are now solving problems that would take an average human like 2 to 4 hours, I think, is the latest for Opus 4.6. And these models can do things faster than humans in some circumstances, but like building code, for example, takes however long it takes, right? And so I think one thing that could be interesting is like how are RL rollouts going to how to train these systems with longer and longer rollouts, right? I think because it means that the training loop is less tight. You have to wait longer between sort of bigger improvements, right?
Eric, I had a question. So I was talking to some mathematicians, and I think some of us agree that the expectation is within a couple of years, when we submit a math paper to a journal, they would also expect us to sort of submit lean code, which sort of verifies that the mathematical arguments are correct, and then the journal just decides whether the result is interesting enough to sort of publish. I mean, exactly what Tao and his collaborators did with the Frida Fisher theorem last year. So do you think harmonic is, if you were to take a guess, like how far do you think harmonic is from me just putting in a PDF in geometry and getting lean code out?
I think that really depends on your field, and I think that's the interesting thing. I think some subfields of mathematics, like the answer is today, right? Like I think some combinatorial arguments,
Right.
the hard thing is not the maths or the thing. It's coming up with the hard argument, and so when a computer sees this argument, it's incredibly easy to translate it to lean, and it requires like very little on the level of theory building, right? But say you work in like K theory or something, like it becomes a problem of like, okay, like now in order to auto formalize this paper, not only do I have to prove all the things, but I also have to build up the whole machinery up to K theory, which isn't in MATLAB, right?
I think that's a great point, but I was thinking about this, and it doesn't necessarily need to sort of have everything in MATLAB before it can write the lean code. I mean, for example, a theorem that's widely accepted by the community, it can also temporarily just state the theorem and put in the sorry, because everybody knows that theorem is correct. So you're quite right. That the ideal situation would be that all the definitions and pre-existing literature is in MATLAB already, but it need not be the case in the next year or so. Like everybody accepts that 2 + 2 = 4, the inverse function theorem is true, and stuff like that. So assuming widely accepted results and putting in sorries for those, harmonic can be this formalizing new arguments in theory in the next couple of years.
Yeah, I think I think we will in the next couple of years be formalizing most things automatically. But I do just want to push back a little on axiomatization. I think it becomes very, very easy to axiomatize something wrong, and it ends up actually being easier for a variety of reasons to just actually write the definition and the correct theorems out than it becomes to write like a completely correct axiomatization of like interesting non-trivial concepts. So I mean, and I think Aristotle is very, very, very good at finding counterexamples within axiomatizations and contradictions and statements. Yeah. So yeah.
Excellent. Another question?
Yes. So you talk about theory building, and I'm wondering, so I'm working on floating point formalizations, and so the lemmas and theorems Aristotle generated are sometimes like too specific to be useful in other contexts, and they also can generate something useful, so it can be reused. So I wonder, like, how do you reconcile to these two situations? Does that make sense? Does that make sense?
Yeah, I think you raise a good point, right? Like, as I say, like these, yeah, as I talked about earlier, like the in the past we generated these theorems by just creating them from an informal proof, right? And so like lemmas of that form are like generally going to be not as general as like say a human would write them. But I think over time trying to build in that human style is part of the challenge, right? Part of the research frontier of like, okay, like how do we write the right lemma? How do we choose the correct thing? And I think this task is harder because it's not like, I mean, you can do reinforcement learning on it, but it's the reward is perhaps messier, right? Like it's more like a creative writing task to choose the right lemma than an easily verifiable, oh, is this theorem proved, yes or no? So yeah, I think part of the
Okay,
reason
yeah.
is that.
I have one more. So you talk about wrong definitions, and so Aristotle generates trivial proofs on it, and you said there's some checks and balances on that.
Mhm.
Can you talk about it a little more? Like how to check the definitions, like something like that?
So for example, one thing we did, and you can see this in the paper, I'd recommend most of the people in the paper
Okay.
is that we had we can check whether, you know, if you give, so if you have an informal proof that's been used to try and prove a statement, and you know you can condition our system that generates proofs with an informal proof, you can sort of see like, okay, did this lean proof actually follow this informal proof? And we've seen sometimes that this can be a measure of quality. Yeah, that's just one example of the sort of things we can do. In
Okay, so it's
general,
in the
I
paper.
think
Yeah. Okay, good. Okay.
I think
Yeah.
it's I think the frontier of AI right now is sort of harness engineering in some way that ends up being like, okay, giving the agent access to more and more actions, but like limiting the harmful ones, right? And I think this sort of falls along the same thing. Like you got to allow your system to the capability to do lots and lots of things because that's how people do their jobs anyways, right? Like, you know, like for some humans, for example, like writing maths without access to Mathematica or like Python is be impossible, right? But stopping the LLMs from shooting themselves in the foot, whether that be by like, you know, wiping your system or just by like doing silly things that don't lead to progress, right?
Yeah. Thank you.
If there are no other questions, let's thank the speaker again.
Thank you, everyone. It's
Thanks, Eric.
yeah, try Aristotle. See you all.
Yeah, thanks, Eric. And thanks for that.
Bye.
Not just like this.